Welcome to our injection molding series. I'm Rachel, your host of today's webinar titled Data-Driven Digital Rebirth and Intelligent Future of Injection. The injection molding industry stands at a critical juncture, shaped by digital transformation and the urgent push for sustainability. Since 1974,富强鑫FCS has been at the forefront of this evolution. It began as a machinery manufacturer and in 2010 proudly transformed into a comprehensive solution provider. So how can we use the data and intelligence to solve inefficiency, energy waste, and quality issues? Today, FCS will show you the path to not only overcome these challenges, but to build a more productive and sustainable future. Let's discover how to make this transformation a reality. Now, I'm delighted to introduce our speaker from FCS, Elaine Lin. She is the product manager specializing in digital transformation for injection molding. In today's session, we'll begin with presentation, followed by Q&A session. Throughout the presentation, we encourage you to submit your questions at any time using the Q&A panel on your screen. Our speaker will address as many as possible during the Q&A segment. Now, let's welcome Elaine for her presentation.
Good afternoon, everyone, and welcome to today's online webinar. My name is Elaine Lin, Product Manager at the Field Application Engineering Center of FCS Group. Thank you for taking the time to join us. Today, I'm excited to share with you how data is becoming the shaping hand of the injection molding industry, guiding photographers toward higher efficiency, more stable quality, and a smarter future. For many factories producing household items and consumer plastic goods, challenges such as rising materials costs, unstable quality, and the pressure to increase productivity are becoming more and more common. Digitalization is no longer just something for large corporations. It is a practical and actionable tool that can help every injection molding factory improve performance and gain a competitive edge in the Southeast Asia market. Thank you again for joining this session. Let's begin our journey into the digital rebirth and the intelligent future of injection molding. To start, I'd like to give you a quick introduction to FCS and share an overview of what we do today. FCS Group was founded in 1974, and over the past 5 decades, we have grown into one of the leading injection molding machine manufacturers in the world. Our capital is $50 million, and our annual revenue reaches $140 million. We have 5 global production bases, allowing us to serve customers efficiently across different regions. Here you can see the overall structure of the FC Group. In addition to injection molding machine business, FCS has several other key business units, including the solar power business, the cable business, and the pet and pilot business. The injection molding machine business unit is the core of our operations, focusing on research and development, manufacturing, and global sales. Our production business and offices are strategically located in Taiwan, Ningbo, Plant 1 and 2, Dongguan, and India, with 3 marketing and service branches across Southeast Asia. This network gives us a strong international presence and enables us to provide localized service and support to customers worldwide. Here you can see our headquarters and the Taiwan plants. It is also the foundation of our global innovation. where new technologies and customized solutions are developed to meet our customers' needs. Next is our Dongguan plant in China. This is our Ningbo plant, located in eastern China. This is our new factory in Hangzhou Bay, which officially began production in 2024. This new factory mainly producing large tonnage and special purpose injection molding machines. Lastly, this is our India plant, which produces injection molding machine ranging from 50 to 850 tons. It serves as a key production and service hub for the South Asia markets, allowing FCS to better support local customers and respond to regional demands efficiently. Over the past 50 years, FCS has built strong partnerships with leading international brands. Our injection molding solutions are widely used in the automotive sector, serving well-known companies such as Honda, Toyota, Tesla, BYD, and many others. This long-term cooperation reflects our capability in delivering stable performances, high production efficiency, and reliable product quality for automotive applications. In addition to automotive, our systems are also widely adopted in the electronics and home appliances industries. We support major brands such as Panasonic, Haier, Canon, and Delta, helping them achieve consistent quality and efficient mass production. These customers rely on FCS for precision molding, stable cycle times, and long-term production reliability. For the household and sports product sector, FCS also supports many well-known brands across Asia and worldwide, from lifestyle products to storage solutions and sporting goods. Our injection molding machine help manufacturers achieve high productivity and cost-effective production. This includes brands like Keyway, Giant, Velo, and many others. Now let's move into part 2. In this section, we will talk about the dual pillar transformation happening in the injection molding industry, driven by both digitalization and sustainability. For many factories, especially those producing consumer household products, these two forces are no longer optional. They have become essential for staying competitive, improving production stability, and reducing operational costs. Many factories still collect production and energy data manually, but this approach is slow, often inaccurate, and provides very limited visibility into what is actually happening on the shop floor. Digitalization is not about replacing people. It's about giving your team better tools. Tools that help reduce waste, improve efficiency, and increases profitability. When the right data becomes transparent and accessible, it becomes much easier to identify problems and make decisions. Digitalization plays a key role in improving efficiency for injection molding factories. While it is aligned with sustainability goals, it gives much clearer visibility to energy use, efficiency losses, and production waste. This transparency allows teams to react fast and make better informed decisions. By pinpoint exactly where energy is consumed, and where efficiency is lost, digitalization supports continuous improvements in operational sustainability and ultimately creates great production value. In injection molding factory, the real business value of data comes not from collecting it, but from analyzing it and applying to daily operations. When we understand the data behind our process, we can transform what used to waste into real value. The value of an injection molding shop ultimately depends on machine uptime and operational efficiency. Every hour of downtime, every reduction in cycle speed, every quality defect, all of this translate into hidden costs. And these losses usually come from these major areas: human resources, energy, and materials. Some issues are easy to notice, like machine breakdowns or scrap parts. But many losses remain hidden below the surface, such as microstops, material waste, setup delays, or small efficiency drops that add up over time. With the right digital tools, we can make these invisible losses visible and turn them into opportunities for improvement and increased productivity. As we move toward digitalization, manufacturers quickly discover that the challenge is not buying sensors or installing software. The real challenge is making digital tools work in actual production. In injection molding, digitalization typically encounters four major bottlenecks. 1. Measurements and monitoring. What should we measure and how should we measure it? Many factories are unsure which parameters are truly important or what instruments are required to capture them accurately. 2. Data collection. What data should be recorded and how should it be collected? A lot of production data exists, but it may not be structured, consistent, or ready for analysis. 3. Analytical modeling. How do we build models and which methods should we use? Turning raw data into meaningful insight requires engineering knowledge, process understanding, and proper machine learning methods. 4. Intelligent decision making. How do we apply the result to real production? This includes adaptive machine control, early warning, and data-driven decision support for continuous improvements. These four bottlenecks explain why many digital projects start with strong motivation but struggle to achieve real, sustainable results on the shop floor. When we talk about digitalization, it's easy to focus on dashboards, sensors, and systems. But digital tools are only meaningful when they help us solve production bottlenecks on the shop floor. Digital transformation usually progresses in stages, from short-term visibility to long-term adaptability. Short-term, IoT and visualization. In the beginning, the goal is simply to connect machines and collect real-time data. Visualization helps us answer basic questions like what occurred. This creates the foundation for a smart factory. Midterm transparency. Once data becomes transparent, we can ask deep questions. What is happening right now and why? This stage brings course-like visibility on site analysis and a clear understanding of process behavior. Long-term, predictive and adaptive. With enough data and proper analytics, factories can predict what will happen next and eventually reach adaptive manufacturing. How should we adjust automatically? This is where sensing technology, scientific modeling data, and the AI-based come together to support decision-making and continuous improvements. So remember, digital systems are tools. The real goal is to solve production problems and increase stability, not just to collect data. After understanding the boundaries in digitalization, the next question is, where should injection molding factory focus its digital transformation efforts? Today, the development of smart injection molding mainly revolves around two key themes. The first theme is smart factory. By connecting machines, sensors, and production systems, factories can achieve real-time visibility, automated data flow, and more scalable production. Human-machine collaboration also helps improve productivity and reduce unnecessary labor workload. The second thing is smart manufacturing. This goes deeper into the molding process itself, integrating information technology with manufacturing technology to enable self-sensing, autonomous decision-making, and closed-loop control. In other words, the process can detect more maladies, adjust parameters, and maintain sustainability automatically. When smart factory and smart manufacturing come together, they create the foundation for AI-driven production, enabling factories to continuously improve quality, efficiency, and sustainability. Now let's look at one of the most important indicators in manufacturing, overall equipment's effectiveness. OEE acts like a health check for machine performances. The purpose of OEE is not to chase a high score. Instead, it provides an objective way to measure where efficiency is lost, so we can reduce waste and improve productivity. OEE is made up of these components. Availability A, how much time the machine is actually running compared to planned time. Performance P, whether the machine is running at expected speed or cycle time. Quality Q, how many parts produced are good parts without defects. When you multiply A times P times Q, you get the overall equipment's effectiveness. A clear, simple indicator that helps factories identify losses and prioritize improvement actions. The real purpose of OEE is not to monitor data or report numbers. It is to help us identify the true root causes of losses and verify whether our improvement actions are effective. OEE allows us to track equipment performance and compare it with similar machines as a benchmark. This helps us understand where efficiency is lost. For example, a factory may have availability 85%, but they are not sure whether the loss comes from breakdowns or changeovers. Performance is 90%. But they don't know if it is caused by long cycles or frequent micro-stops. Quality 99%, but scrap may still hide issues such as material variation or process instability. Without understanding the underlying causes, improvement is impossible. OEE gives us the clarity to ask the right questions. What is the real cause, and what corrective actions should we take? After understanding OEE and the importance of identifying losses, We now look at the two key time basis factors in injection molding: cycle time and changeover time. Cycle time is the time from one good molded part A to the next good part A. It reflects the stability and efficiency of the molding process. Changeover time is the time from the less good part A to the first good part B. When switching models and products, this period often has losses such as trial shots, adjustments, warm-up cycles, and unstable conditions. Both CT and CO always exist, but the question is, do we have a clear standard? And how do we verify that standard is actually followed? When CT becomes abnormal, it usually indicates issues such as slower cooling, inconsistent injection speed, or microstops. When CO becomes too long, it often reflects problems in mold conditions, setup preparations, or unstable first shot quality. So the important questions for the factory are: what is the root cause? And what countermeasures should we take? Next, in many factories, molders often assume that two machines with the same tonnage or similar specifications will produce the same molding results. For example, here we have machine A and machine B. Both are 200-ton clamp force. Both have a 140-bar hydraulic pump, a general-purpose spool, a 225mm linear shot capacity, and the same type bar spacing. On paper, these two machines look identical, but in real production, their molding behavior can be very different. Factors such as spool diameter, injection rates, actual response speed, pressure build-up characteristics, and even wear conditions can cause significant differences in filling, packing, cooling, and final part quality. This is why specification level consistency does not guarantee process level consistency, and it's also why significant molding and digital monitoring are so important. They help us reveal differences that cannot be seen from machine specs alone. Even when two machines have the same clamp force and similar specifications, their actual injection behavior can be very different. One of the biggest differences comes from the spool diameter. In this example, machine A uses a 44mm spool, while machine B uses a 50mm spool. Both machines are set to the same 50% injection speed, but the actual linear injection speed is completely different. The 44mm spool produces a higher melt flow speed, about 140mm per second, while the 50mm spool produces a slower melt flow speed, about 100mm per second. These differences in melt flow speed leads to different flow viscosity, different filling behavior, and ultimately different part quality. This is why using the same percentage setting does not guarantee the same molding results. To achieve consistency between machines, we must compare real injection viscosity, not just the percentage shown on the screen. Now, that we've seen how different spool sizes create different melt flow speeds. The next question is, what does the differences actually do to the plastic melts? Here we can see that as the injection velocity increases, the melt viscosity decreases. This means the melt flows more easily and at higher speeds. If two machines are running at different actual velocities, Even if the setting looks the same, the melt inside the mold behaves very differently, giving different filling patterns, pressure build up, and the packing results. This is why achieving consistent molding requires more than machine parameter percentages. We must look at the actual melt behavior, which is driven by data such as viscosity curves and flow characteristics. Even parameter setting, whether it's speed, pressure, or switch cover points, must be based on data-driven rationale, not guesswork or habits. This forms the foundation of scientific molding, ensuring repeatable and stable production from machine to machine. Now, let's see how injection speed affects melt viscosity and the flow behavior. The next question is injection speed the only factor that affects consistency between machines? The answer is not at all. In this example, machine A and machine B are still using different screws and therefore producing different melt flow speeds, even at the same 50% setting. But speed is only one piece of the puzzle. Other factors also affect filling behavior and molding consistency, such as the screw design, the injection rate capability, the machine response time, the compressibility of the melts, and even the hydraulic or electronic system characteristics. So even if the setting on the controller looks the same, the actual melt movement inside the mold can be very different. This is why relying on percentage-based setting is not enough. To truly achieve machine-to-machine consistency, we must understand the real physical behavior, not just the parameter on the screen. Earlier, we talked about how melt behavior affects consistency in molding. Now, let's look at another key factor that directly affects cycle time and the part quality: molding cooling water flow rates. A cooling system should be designed to achieve turbulent flow, not laminar flow. This is because water flow rate has a greater impact on cooling efficiency than mold temperature itself. In many factories, the cooling system is often the weakest link. Poor channels design, scaling blockage, or undersized pumps frequently causes unstable water flow, which leads to inconsistent mold temperatures and unstable cycle times. When we review molding conditions, we usually see mold temperature recorded, but very few factories record actual mold water flow rates. This means we may think the temperature is controlled, but the cooling efficiency is actually fluctuating. To ensure stable molding, we must confirm, is the cooling system delivering enough flow, and is the flow turbulent and not laminar? Improving cooling flow is one of the most cost-effective ways to reduce defects and shorten cycle time. Up to now, we have focused on the machine and the process level, how speed, viscosity, and cooling affect stability and cycle time. In this part, I'd like to zoom out the factory level and show how we connect all of the through industrial IoT. FCS provided an industrial IoT platform based on our MF system. It connects injection machines, equipment, and even logistics devices into one of integrated solution. Around this platform, we offer several key application systems. MES, Manufacturing Execution System. manages production orders, machine status, molding parameters, and the traceability on the shop floor. WMS, Warehouse Management System, handles material in, out, inventory locations, and supports real-time stock control. EMS, Equipment Management System, monitors machine health, maintenance plans, alerts, and OE analysis. SRM, Supplier Relationship Management, coordinates with suppliers for materials delivery and purchasing information. EDI, Data Exchange Platform, links to ERP and other IT systems, so lets data flows automatically instead of relying on manual reports. For an injection molding factory making household products, this means real-time visibility of production, materials, quality, and equipment, all connected in our system, supporting faster decisions and more stable operations. As we come to the end of today's session, I'd like to step back from technology for a moment and remind all of us of something fundamental. We often say quality is created through design and manufacturing, not through inspection. If that is true, then what about our approach to digitalization? When we collect data, is the purpose simply to recall the current status, or should it guide us toward improvements, stability, and better decisions? In other words, are we putting the fish on the tree or in the pond where it belongs? The right tool must be used in the right place. Digital systems, sensors, and dashboards are meaningful only when they help people work better. Tools should serve people, not the other way around. So as we move forward with digital transformation, let's return to first principles. Focus on real problems, design smart processes, and use digital tools to simplify the ability of our teams, not to overwhelm them. Thank you all for joining today. I hope this sharing brings inspiration for your own journey towards smart injection molding.
Thank you, Elaine, for your insightful sharing. A friendly reminder to the audience, by actively participating and asking questions, you could be in the running to win some fantastic gifts. Wishing you all the best of luck. Now, let's begin the Q&A session. We can see many questions have come in. Now, let's welcome Elaine to address the questions. Elaine, please turn on your microphone and camera for this session.
Hello, everyone. Before we wrap up, let's take a moment for some Q&A. Thank you to everyone online for thoughtful questions. In the next few minutes, I will go through them one by one and share some brief answers. The question one, if two machines have similar specifications, why are the molding results still different? Even when machines look identical on paper, their actual injection behavior can be very different. Differences in screw diameter, injection rate capability, response speed, and wear conditions all affect melt front velocity and filling behavior. That's why using the same parameter percentage doesn't guarantee the same molding result. We must compare real physics conditions such as actual injection velocity. The question two, why do we need to focus on melt viscosity and injection velocity? Melt viscosity directly affects flow behavior, filling patterns, and the pressure transfer inside the cavity. Injection velocity determines the shear rate, which determines viscosity. If two machines run at different actual velocities, the melt behaves differently, even if the settings look the same. Understanding viscosity is the foundation for scientific molding. The question 3, why do you say mold cooling water flow rate is more important than mold temperature? Cooling efficiency depends more on water flow rate than on temperature. If the flow is too low or in laminar mode, heat transport becomes unstable, leading to inconsistent cycle times and product quality. Many factories record mold temperature but do not record flow rate, which hides cooling problems. Ensuring turbulent flow is one of the most cost-effective ways to stabilize production. The 4, what's the real purpose of OEE? OEE is not about chasing a high score. Its purpose is to reveal where losses occur, downtime, slow cycles, micro stops, or defects, so that we can identify the root cause and take corrective action. Without understanding the cause, improvement is impossible. The 5, how should the factory start digital transformation if resources are limited? Begin the short-term stage, connect key machines, collect basic production data, and visualize the current conditions. Once you have transparency, you can identify bottlenecks and gradually move toward predictive and adaptive functions. Digitalization should focus on solving real production problems, not installing all systems at once. Let's conclude my presentation for today. I will now hand the section over to Rachel.
Thank you. Thank you again, Elaine, for invaluable insights today. Our discussion has sparked so many great questions. If you have more, please feel free to contact our speaker using the information provided. The conversation can continue offline. This concludes FCS session for today. To stay updated on the latest trends in injection molding solutions, you can discover them at slcprj.com. Be sure to follow us. Your feedback is important to us. As we say goodbye, a quick survey will pop up on your screen. It only takes 30 seconds to complete and will greatly help us improve future events. Thank you everyone for your participation, and we look forward to seeing you at our next webinar.